This is the screencast for section 3.1, example 1. We're going to look at exponential and logistic functions. Now, logistic is not logs. I know you've heard of logs before. I think you might have done logs in Algebra 2, but this is logistic functions, something a little bit different. We'll go into logs in later sections. So first of all, let's define what an exponential function is. An exponential function is written in the form f of x or y equals a, so a number in front, times b, another number, to the exponent of x. So x has to be the exponent. What else? A has to be non-zero. That'd be very boring if a was 0, because then 0 times anything is 0. You've got a horizontal line on the x-axis. B has to be positive. If b was negative, the graph would be all over the place because negatives to even powers are positive, negatives to odd powers are odd. It'd be messy. And b can't equal 1. Also, if b would equal 1, that would be a very boring graph because 1 to any power is still 1, so the graph wouldn't change at all. The constant a is called the initial value of f. Basically, your y-intercept is your initial value when x equals 0. It tells you that right there. And b is called base. There are two types of exponential functions. There's an exponential growth function whose base b is the growth factor and b is greater than 1. So an example of growth, we'll go with growth over here, would be y equals, I don't know, 4 times, let's see, b has to be greater than 1. A can be anything, as long as it's greater than 0. But if b is, let's say, 3 to the x power. I don't know exactly what that looks like, but I do know that most exponential functions are going to look like this. Exponential growth functions look like this. This y-intercept, or initial value, let's see, if I plug in 0, 3 to the 0 is 1, 4 times 1 is 4, so that's 0, 4. Now this is not an exponential growth function because it is going up. Going up does not mean growth. I know, sounds weird. But growth means that the rate of change is increasing. See over here, the graph is going up but kind of slowly, and then it's going faster and faster and faster, and now it's growing super fast. It's increasing super fast. That is exponential growth. Exponential decay is when your b value is less than 1 and of course greater than 0 that we know from the other definition. So a decay function might be y equals, we can still use 4 out in front, but now we'd use something smaller than 1. So let's try 1/3 to the x. Again, not totally sure what this looks like, but exponential decay is going to go that direction. Now this y-intercept, or initial value, if I plug in 0, 1/3 of the 0 is 1, 4, still 0, 4. 1 times 4 is 4. This is exponential decay because its rate of change is decaying. See, it's changing very quickly here. It's decreasing very, very quickly, and now it's slowing out, it's leveling out. So its rate of change is decaying. If you notice, these look like a horizontal flip over the y-axis. Well, if you remember from your log properties, or excuse me, your exponential properties, this decay formula can also be written as y equals 4 times, let's see, 3 to the negative x power, which would be a horizontal flip over the y-axis. Exactly the change between this growth and decay problem. So let's look at an example. We're supposed to identify the exponential functions. So let's determine which ones are exponential, I guess. This one is definitely exponential. I'm going to be more specific because this is notes and I want to teach you something. The base is 3, so this is going to be exponential growth. Now its growth factor is 3. Now that doesn't mean that it is growing by 300%. It means that its rate of growth is actually 200%. We'll learn a little bit more about that in the next section. Its growth factor is 3, meaning that tomorrow you'll have 300% of what you have today. So in other words, you have 100% everything you have today plus 200 more. So it's growing by 200%. Let's take a look at another example. B, oh, that's not exponential. That is not exponential. It's not growth, it's not decay. X has to be in the exponent. That's not the case here. Now C's weird because our A value is negative. We call this, so first of all, looking at the B value is greater than 1, so this is an exponential growth. But because the A value is negative, we're going to call this a reflection of growth. Specifically, it's going to reflect where? That's right, vertically over the x-axis. So a reflection of growth, its growth factor is 1.5, which means its rate of growth is 50%. 0.5. So tomorrow you'll have 150% of what you have today. All of what you have today plus another 50%. It's growing by 50%. Now D is tricky. It's tricky. Remember we talked about the negative exponent and the horizontal flip over the y-axis? So the first thing I'm going to do to part D is I'm going to rewrite this as k of x equals 7 times. Now instead of 2, I'm going to write this as 1/2 to the x power. Now I can see that that is exponential decay because its base is 1/2. And that means the growth factor, no, decay factor this time. Oops. Decay factor is 1/2, which then means its rate of decay is 50%. I'm only going to have half of what I had today. E, there is absolutely no variable. 6 to the pi, so 6 to the 3.14, I don't know, whatever 6 cubed is, and then times 5. It's just going to be a horizontal line at some really large number. So this is not exponential. The now try problem number 1 says which of the following are exponential functions? For those that are exponential functions, state the initial value and the base. For those that are not, explain why not. So number 1, y equals x to the 8th power. That is non-exponential. The variable needs to be in the exponent for exponential functions.